Okay, we're going to talk about logarithmic functions. Logarithmic functions are inverses of um, exponential functions. That's how we're going to define logarithmic functions, as inverses of exponential functions. Now, the thing is, there are many exponential functions. There are exponential functions on base 2, on base 3, on base e, on base, any base that you want. Well, I shouldn't say any base, because the bases have to be positive numbers and the bases cannot be 1. So if you have y equals 2 to the x, we saw that in a previous video, about 2 videos ago. And this is a quick sketch of the graph going through 0, 1. This function has an inverse. It is 1 to 1. It passes the horizontal line test, and of course it passes the vertical line test. And so it is 1 to 1. It has an inverse. The inverse is the reflection over the y equals x line. So this diagonal line, if you have a line going diagonally 45 degrees, if you reflect that over this line, then you end up with the inverse. And the inverse is very useful because it tells us when we will be able to get an exponent that gets to an output. See, part of the motivation for this is to be able to solve equations like this. 2 to what power is equal to 3? You know, 2 to the 0 is 1. You know, if we can make a table of this with an input x and then an output 2 to the x, 0 is 1. 1 gives us 2. And then 2 gives us 4. So the question is, okay, what number, question mark, is going to give us 3? And the answer is not 1.5. This is exponential behavior is not proportionally, it's not proportional. Very important. Things are not going to work proportionally. So there's an input that gives us 3, and we want to know, for example, what is that input? And that's one reason why we want to be able to use logarithms. So we have to be able to undo the 2 to the x. And so far, we don't know how to do that. We know how to undo squaring by taking the square root. We know how to undo an addition by subtracting. We know how to undo a multiplication by dividing. We know how to undo a division by multiplying. How do we undo an exponent like this? That is not obvious. That is not clear. That is not trivial. So from a graphical point of view, we draw the inverse, which is going to look like that. So this side on the left becomes, well, as sort of a side going down. The horizontal asymptote becomes a vertical asymptote. And instead of going through 0, 1, this new graph is going to be going through 1, 0. In fact, all the logarithms go through that point. Now, there are many exponential functions. There's 3 to the x. There is 4 to the x. There's 1.5 to the x. There is any number, as long as that number is positive, and as long as that number is not 1, we have millions and millions and millions and billions of exponential functions. And consequently, there is going to be correspondingly millions and millions of logarithms. And we got to be able to tell them apart from each other. So the name for this inverse is going to be the logarithm. But there's going to be many logarithms depending on the base. This is called, of course, the base. Base of the exponential function is 2. And so the logarithm has to be differentiated from the logarithm in base 2 has to be differentiated from the logarithm in base 3 or 4 or 5. So the name is a little awkward. The name of the function will be whoops, that's an O, G, with a little 2 on the lower right corner. That's called a sub-index. So that is the call name of the function. And then we many times put the input in parentheses. So the function will be y equals logarithm base 2 of x. So this is the name, and we cannot really undo this. You know, functions have different names, such as f. You know, a lot of the functions we use in algebra have the name f because it's an abbreviation for function, or also y. So let me write down names of functions, you know, such as f, y, you know, you can call it g, etc. Some functions have a longer name, such as sin for sine of an input, whatever the input is, sine of x, or cosine of x. Some functions have a funny exponent to them. So for instance, the sine inverse of x is a function that undoes the sine of x. Yeah, it's, well, undoes the sine. I didn't intend to put an x in it. It's just because I want to focus on the name of the function, not on the input itself. Um, this dries up, and if you don't use it often, and then um, so I guess I got to make more mistakes, so I use it more often, and that way it doesn't dry up. Anyway, um, and here I neglected to put a parenthesis, but we usually have f of something, you know, sine. So this is a funny name because not only it has 3 letters, the name sine, and it has the exponent, you know, sin, and then the exponent, and then the input, and you cannot really break this up. It's not like a we're not multiplying s times I times n, you know, or 1 over n. No, 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 no. This is the name. The whole thing is the name. You cannot break it up into anything. It's just a long name of a function, as opposed to a short name of a function. We got a long name, and even that little upper index or exponent is part of the name of this function. So likewise here, this is the whole thing is the name of the function, including that too. It's kind of like a middle name letter, you know, like Joe R. Smith. So that means the R is the middle name. You know, it could be Richard, it could be, I don't know, anything. So pretend that is sort of a middle name, and the reason why we have that is because we want to differentiate it from another function that has the same name. I was going to say the same first name, but kind of the same thing, with a different base. So for instance, this is a logarithm base 3. This is the name of the function, and then we put the parenthesis for the input after that. Many books don't have the parenthesis. In mathematics, we do value simplicity. You know, the less within reason, the better. And I see their point. I don't think that is necessarily a bad point. However, when we are learning this, it is better to maybe exaggerate a little bit the parenthesis, so we say, okay, that's where the input goes, and this is just the name. Otherwise, what I have noticed in the past is that students who are still learning this, there's nothing wrong with them. It's just when we are learning something, we are still getting to know what's going on. When they see this, they think that x is the exponent of the 2, and that's not the case. So that's one of the things I want to emphasize. We are not doing 2 to the x. No, 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 no. We have a name for the function. See, and that's why I prefer not to use the notation without the parenthesis, because things can get mixed up one with the other. It's like if we were writing a sentence in English without spaces, then where does the word end? Where does the word start? You know, it can create some confusion. I should try that just to see how it looks, you know, to see how bad it is. You know, the cat is gone. I just came up with that. So if I put the cat is gone, I don't know. Some people, I don't know. Anyway, the point I'm trying to make is if you put this without the parenthesis acts sort of like as a space in the sense that it's telling us, okay, that is the input, and this is the name of the function. So I want to make sure that that is clear. This is not so clear, especially for somebody who is still getting used to all of this. Um, uh, yeah, and there's nothing wrong with that. Getting to know something is not a is nothing. There's nothing wrong with that. Quite the opposite. Getting to know something is a virtue because we are expanding our mind. So, but initially, it is frustrating when we are learning any new thing because we don't know what's going on. You know, there other people may know and we may not know. Anyway, so this, in my opinion, my personal opinion, it is confusing. Um, um, little confusing in my opinion. Okay, it's better to put the parentheses. So in classes that I teach, other classes that I teach, I tend to put parentheses, you know, sign of X. A lot of books don't do that. They just put SIN and then X, maybe a little space in between. But again, I prefer to make things perfectly clear rather than assume that everybody knows what's going on. Okay, so let's go back to this. Let's label it as example one. So we're going to start with a little bit of the graph. Um, and let's focus on y equals 2 to the x. The corresponding inverse function will be y. We're going to call it y, but that's a different function. So those are two different functions. Logarithm base 2 of x. Okay, so they are inverses of each other. The graph of this, as we know it, goes this way. One of the points here is 0, 1. Another point is 1, 2, because when we do 2 to the 1, we get 2. And then another point here is negative 1 comma a half. Now, the logarithm, which is the inverse of this, please pay attention because this is important. A lot of students say, I don't know anything about logarithms. Well, here it is. Here it is. If we ask, what is the logarithm in base 2 of 1? The answer is 0. Why? Because the logarithm undoes. So the 2 to the x function does 0 to 1, does 1 to 2, does negative 1 to 1 half. So we're going to undo that. We're going to undo the 1. So you should end up with 0. Undo the 2. So the logarithm base 2 of 2 is 1. Another point up here with whole numbers would be 2, 4. So the logarithm in base 2 of 4 is equal to 2. And let me do one more. Logarithm in that direction. Base 2 of 8 equals 3. Why? Because 2 to the third equals 8. Notice that we're not doing 2 to the 8 at all whatsoever. If we were using the notation without the parentheses, then we would be thinking, oh, 2 to the 8. In fact, that's a good multiple choice question because then I could say, hey, what is 2 to the 8? And then somebody could say, whatever 2 to the 8 is. I know 2 to the 5 is 32, so I don't know, 500 and something. But that's not the answer. The logarithm in base 2 of 8 is 3. Why? Because, well, there's a couple of reasons. The reason graphically is because when we plug in 3 into the exponential, we get 8 out. See, if you have x and 2 to the x, 1 goes with 2, 2 goes with 4, 3 goes with 8. So we want to undo this. We want to go the other way. And that's the reason, because if you do 3 on the original 2 to the x function, we end up with 8. So undoing that gives us, the reverse. That has to be true when the base is 3, rather when the base is 2. If the base was something else, such as 3, then this is off. Then we got to figure out what it is. All right, the logarithm in base 2 of 1/2 is -1. So that is very interesting. If we get a number that is between 0 and 1 in the input, the output has to be negative. But there is a catch to that as long as the base is greater than 1. So there's a lot of moving parts here. The base, the input, the output. There's a lot of things that we have to take into account. Become very familiar with logarithms. I think logarithms isn't that difficult. I shouldn't say that it isn't. It is a little difficult, but it is something that we can overcome in a reasonable amount of time, in an afternoon. Now, I know that is relative, you know. Some people will do this in 10 minutes. Some people like me, and I'm not being, I'm not exaggerating. I typically take a long time to figure things out, and I typically take a long time to understand something. I usually understand it really well, but that's just, I'm just saying that to make myself feel better. But in general, it does take me a little while to really get to know something, such, you know, such as logarithms. But generally speaking, it is something that in one afternoon we can really get to know pretty well. Now, this is a trick. A lot of students get to this point and say, okay, I got it, but they don't practice. And we cannot perform well, we cannot do well in mathematics if we do not practice. So we really want to practice this. Oftentimes, it is not a matter of understanding the concept. I think many students understand the concept, but then they freeze when they see a problem because they haven't practiced enough of that concept. All right. So we can do a few more of those. Logarithm in base 2 of 1/4. Okay, so 2 to what exponent gives us 1/4? Well, 2 squared gives us a 4, but this is the reciprocal, and the reciprocal means negative exponent. So we are obtaining the output of this as the exponent that we place on 2 to get the 1/4. And in this case, it is -2. Yep. Then we have a question. What is the logarithm in base 2 of a number? Okay, so we know that 2, logarithm of 2 gives us 1. Logarithm of 4 gives us 2. What about the logarithm of 3 in between? That is not obvious. This is not, this particular example is not obvious. Again, obvious is a funny adjective because what is obvious to one person is not obvious to the other, and you know, it's relative. So, but it's not straightforward. That's probably better than obvious. It is not straightforward in the sense that from a nice little table like this, we can figure it. No, we don't know. We know that the answer is going to be between 1 and 2. Now, if you look at a calculator, we got logarithm keys. This is a logarithm, but this is a natural logarithm. So those are two logarithmical keys, but we don't have a logarithm in base 2. So we cannot figure out logarithm in base 2. Actually, I'm going to tell you how to do it. Let me tell you a little more. Okay. And I don't know why. It shouldn't be that hard for an engineer who worked on this already to come up with a key, with a logarithm where you plug in the base and then you plug in the input. I don't know why engineers didn't do that right up here. Maybe it is in the menu and I just don't know, because there's many things that are not on the keyboard but are in the menu. If you there's ways to access it and calculators like this. But one of the things I want to bring up, so we're going to come back to this in a moment, but the reason why I'm bringing this up is because calculators don't have logarithm base 2. or logarithm base 3, or logarithm base 4. They have two logarithms. Okay, so let me make a note here. So we're going to keep this hanging. We're going to leave that hanging in there. Just what is the answer? We don't know yet. We will find out. We will come back to that. See, I'm building up suspense. Now you're thinking, now I have to watch the end of the video because he's not going to tell us that yet. Isn't that a good strategy for me so that you keep watching the video? Anyway, oh, the calculators have only two keys, two logarithm keys about logarithms. They have log without a base, no base, and then ln. So those are the only two keys they have. They don't have a logarithm base 2. Okay, so let's go to those two. And I don't know why that is the case. In this day and age, you would think that shouldn't be an issue. LOG. Before I continue, let me write a note, a quick note to everybody. LOG, it doesn't matter how you write this down. If you put LOG with capital letters, same thing. If you put it with a script, you know, LOG. If you combine L, O, G, all of them are logarithms. It doesn't matter how you write it. It is the same. Just try to be consistent. Even I'm not consistent sometimes. I start, I don't know. So just be aware. It doesn't matter what kind of font we use. It is the same, or capital letters or lowercase letters. Sometimes that matters, but in this case, it doesn't. So what is the logarithm? If there is no base, then what is the understood base? So no base, let's clarify that. No base means common logarithm that is base equals 10. So that means logarithm in base 10. Yeah, which means we have the inverse of 10 to the x. So if you have y equals 10 to the x, we are familiar with this, and we go this way, and we got 0, 1, and then we're going to end up with 1, 10, and then 2. So if we draw a table of the exponential function 10 to the x, we will have x and then y equals 10 to the x. So 1, 10, 2, 100, 3, 1,000, and so forth. Now, the inverse will be the logarithm in base 10. That's the name of the function of x. But everybody agrees that if we don't put 10 down, it is assumed, it is by default, that is the base we're going to be using. Now let me double check. If I'm correct, let me clear that up. If we put logarithm of 1,000, close parenthesis, okay, so I'm going to figure out what the logarithm of 1,000 is, and we better get this answer that I'm pointing to. Sure enough, we get 3. So this confirms what I am establishing, that the logarithm without a base means we have logarithm base 10. We can do another one. Logarithm of 100 is 2. Logarithm of 10 is 1. Logarithm of 1. Logarithm of 1 is 0. And then we can do logarithm of 0.1. So 10 to what power gives us 0.1, and that is -1. Okay, so get to know your inputs and your outputs. The graph of the logarithm is going to look like this. It is going to go through 1, 0. There's a point here. So this is not proportionally correct, of course. 10, comma, 1. Why? Because 110 is on it. Another point with whole number coordinates will be 102. So we got to go all the way up to 100. So this is totally, completely not to scale, because it doesn't make sense that from here to here you get to 9 units. We add 9 units from here to here because we start out with 1. So from 1 to 10, we got 9 units. From 10 to 100, we are going 90 units. It doesn't make sense. So this is not proportionally correct. If we were drawing this more proportionally, the graph will flatten out very, very quickly. It will never be completely flat. It will always have an increasing slope. However, the graph will look very flat very quickly. That's why they say a lot of the learning we do is logarithmic. The curve is logarithmic. So at first, the graph is a little bit steep, but then as we go on, a lot of things for that matter are logarithm. It takes longer, much more effort to learn a little more. To get something more perfect takes more, not double the work, but many times triple or 4 times, or in this case, 9 times the work to get to the next level up. That's why a lot of things that are very, very perfect are very expensive. To make something relatively cheap, you're getting a lot of money for your quality. But to increase the quality, you got to spend a lot more money. Learning also goes that way. Learning the first things it goes relatively quickly, and then learning more, perfecting your learning takes much more effort. I'm grossly generalizing. Not everything is exactly this way, but this is a gross generalization. And then here we have points such as 0.1 or 0.1 comma -1 and so forth. And there's an asymptote. So this curve gets closer and closer to the asymptote, in this case, without crossing it. And that means that we can never, ever have a logarithm of 0. So logarithm of 0, if you put in the calculator logarithm and then you plug in 0, let's do it. Doesn't cost us much to do that. Logarithm, and then 0, and see what the calculator says. Error. We cannot do that. That is totally, totally wrong. Yeah, we cannot do logarithm of 0. Why not? Because the graph doesn't reach 0. And if you put -1, that's even worse. In calculus, we do use 2 branches, this and this, by adding an absolute value. So we actually look at 2 sides, but there is actually 2 logarithms, 1 here and 1 there. If you put an absolute value on the input, then that creates 2 branches, but that is a different story. Okay, so this is what is called the common logarithm. If the base is 10, then oftentimes we do not write down the base, and the default base is 10. So I want to go back to this question. I'm sure since you've been watching the video, you want to know this. How do we get the number between 1 and 2 that gives us 3? 2 to what exponent gives us 3? And the answer is not 1.5, by the way. Yeah, 1.5. If we do 2, so let's quit. Okay, so if we do 2 with the exponent of 1.5, yeah, that doesn't give us 3. It gives us less than 3. We want 3. It's not even that close to 3. So that's not going to work. Yeah, but so what is the number? Well, the number is logarithm base 2 and 3, but the calculator doesn't have logarithm base 2. So we're still thinking how to do that. Well, there's a formula that says it is called the change of base formula. change of base formula. And it turns out that we can change any base into another base. There's a catch to it, though. So let's say you have a logarithm in any base A or B, yeah, of x. You can always change it to another base, so logarithm base A, as long as we divide by the logarithm of B in the same base. There we go. So logarithm in base B can be written as a logarithm on a different base as long as we divide by the logarithm of the base of the original base. I know this is a little confusing, but let me apply it. So we want to know logarithm in base 2 of 3. We want to know that. And the calculator doesn't have a key for that. No problem. Based on this formula, we can say that is the logarithm in base 10. No need to write it down when we are dealing with logarithms of 3, as long as we divide by the logarithm on the same kind of logarithm of the previous base. This is the answer. This is the exact answer. By the way, that is exact. And then we can figure this out on the calculator, and the calculator will give us a good approximation. So if we have logarithm of 3, close parenthesis, see, the calculator does have a, well, this calculator has a nice parenthesis telling us, okay, here's the input. When you finish putting the input in, close the parenthesis, divide by a logarithm 2, close parenthesis, and there is our solution. Let me see this a little. So about 1.58 is the approximation, 1.58, not exactly 1.58. Notice the approximation symbol. And that is over 2 decimals, the closest we can get. So if we do 3, no, not 3, 2, with an exponent of 1.58, then we're not going to get 3 because that was an approximation, but we get something that is very, very close, 0.98, yeah, 2.98, which is really, really close to where we want to be, 2.98. Yeah, so that's, if we wanted to know, to have the exact answer, or if we wanted to have more decimals, we would type more of those decimals, and that will get us even closer to 3. All right, so that's how we change the base of logarithms, and that's why, one of the reasons why the calculator does not have a logarithm in other bases, because all you need is one base. Actually, you don't even need 2 bases, but we have 2 keys. One will do, and by using that base, we can find logarithms of any kind. Having said that, I don't know why. Maybe there is. I think there is somewhere in the menu. I'm going to guess there is, where you can actually get logarithms of different bases. But I don't know. I don't know. The other logarithm that is important is the natural logarithm. The natural logarithm abbreviation is ln. Okay, so we have the natural logarithm, and the abbreviation for it is ln. You know, sometimes I put together like that, or L, and there's many. Again, it doesn't matter what font you use. All of them mean natural logarithm. So the natural logarithm is just a logarithm like any other logarithm, except that the base is e. So the base is the number e, which is about 2.72. It's not 2.72. It is close to that. Um, so if we did, let me find E here. Yeah, it is this guy. Then that's E with all of its glorious decimals. Up to that point, there's many, many, many decimals after that. So it does have an infinite number of decimals, and they do not cycle. They don't come back to a cycle ever. So there is the number E, and the base we use is E when we have natural logarithm. And somebody might ask, well, that's kind of weird, odd. Why do we use that? My answer, my personal answer, is because it makes calculus way simpler, way simpler. See, this is off topic. This is not algebra. I want to get just into calculus for half a minute or so. If you find the derivative, so dealing with derivatives, for instance, of y equals 2 to the x, the derivative would be the natural logarithm of 2. See, I'm not going to put parentheses because I don't have a lot of room here, times 2 to the x. So that derivative formula, I'm putting an arrow to indicate that is the derivative of this function. In this case, that formula is cumbersome, to have to multiply natural logarithm each time you're doing derivatives. Oftentimes we have to do multiple derivatives, one after the other. So we have this coming up over and over again. Compare that with y equals e to the x. The derivative of y equals e to the x is e to the x. So this is a very clean derivative. It's very smooth. There's nothing to do to multiply by. Here, it gets more complicated. So it is by far more convenient to use e because the derivatives don't add things to them that make the computations cumbersome. So in my opinion, that's a really good reason why we want to use e as opposed to any other base, because it makes the calculus computations that much easier. And it turns out that you can also change bases of exponential functions. Yeah. One of the things we want to make sure we understand is that they are inverses of each other. So the role of being inverses. That means that if you do, say, 2, and you put as an exponent logarithm in base 2 of some weird number, 17, that's not that weird, but let's label this as an example. Let's label it as example 3a. For just 3, we can just go down the numbers this way. So let's say we want to simplify this. Now, mind that the base of the logarithm matches the base of the exponent, or the base of the exponential expression. So that's going to be 17 because they undo each other. They undo. The 2 to a power moves to one side of the table where we have the exponents, but then the logarithm brings us back the other way. Similarly, if we have the logarithm in base 2 of 2 to the 17, again, this undoes the 2 to the 17. So we just end up with 17. Either way you do it, they undo each other. Make sure the bases are the same. Oh, I didn't come back to this one, and I remember I told you we did go back, but I didn't quite fill that in. The answer is about 1.58. So the answer is about 1.58. 58. Yeah. So that is the undoing. I can give you many more examples, but 5, but they would be about the same. Sometimes we write them down with letters. So the logarithm in a generic base b of b to the 59, well, that is going to be, as long as the bases are the same, we get 59. And the other way around too, if you have b, okay, this expression is interesting because the exponent is meant to be written with a smaller font. So log should be smaller than the font or the size of the b. Those letters are supposed to be smaller because they are exponents. But then that has an index, which is even smaller. So, they get smaller and smaller. Things get smaller and smaller as we go along. So logarithm base b. B is an index of logarithm, which is written with a smaller font. And then logarithm is already smaller than the b. Anyway, of 53, there we go. So again, they undo each other. So the answer is 53. Now, sometimes it is true that this is what's going on, but it's not obvious. Let me give you another example. Say you want to find the logarithm, the common logarithm. So what is the base? 10 of 1,000. Let's make it bigger, 10,000. Okay, 10,000. The base is 10, so keep that in mind. So if we could write this as 10 to a power, then we are all set. So this is logarithm in base 10. Even though there's no need to write it down, I write it down many times so I don't forget what it is, or to emphasize what it is. And then we realize that 10,000 is the same thing as 10, 2, 3, 4 zeros. So that's to the 4. Now that we have the same base, it is very clear that the answer is 4. Many, many books have problems like this. Don't use your calculator. Your calculator will give you the right answer, but don't use the calculator, because what you are meant to be doing is to figure out, oh, this is a power of 10, and consequently they undo each other, so the answer is 4. If you just punch numbers on a calculator for this kind of problem, then we're we're defeating the purpose. It's like asking somebody to run 3 miles, and then they get in their car and they go around the block 3 miles, and they come back and say, I ran 3 miles. No, that's not the point. Running 3 miles means with your feet. So the same thing is here. If we ask students to do this, and many, many books have those kind of problems, they're not saying just punch it into a calculator, because then we are not even thinking. We mean, okay, figure out how to write this in terms of that, so that you can so that we can tell what the exponent is. Let me give you another example. So 7, 8, yeah. Let's say you have the logarithm in base 2 of 1 over 32. Okay, that's a typical kind of example. Okay, so I have to be able to write 32 as a power of 2. So this is the same thing as logarithm in base 2 of 32. Okay, 2 times 2 is 4, times 2, 8, times 2, 16, times 2 is 32. So we go 2, 4, 8, 16, 32. All right, so that is 2 to the 5, but there's more to it. This is a reciprocal situation, so we have actually a negative exponent. Aha, now we got the same base. So the answer should be -5. Can we punch this into a calculator? Sure. Now I'm curious, but we have to do the change of base formula. Now, if you do this, put things on the calculator after the fact, yes, by all means, go ahead, do that. Because then we are checking, we are reinforcing what we are learning. But to get this answer from the calculator, that's not a good thing. That, yeah, anybody can push buttons, I think. Okay, so logarithm base 2. So we gotta do logarithm of 1 over 32, close parenthesis. But we gotta compensate for the fact we have to use the logarithm in base 2. So we're gonna divide by logarithm of 2. And I think we're supposed to get -5. Sure enough, we get -5. All right. So this confirms that that's the answer. All right. But the point of the problem is to figure out how to rewrite this in terms of 2 with a power, with an exponent, and then voila, we get the answer. Those two undo each other, and then we get the answer. Logarithms are not a bad thing. They are a good thing. Oh, one of the things we ask is to write a logarithmical equation into an exponential form and vice versa. So exponential equation, we want to be able to transform them into logarithmical equations. And vice versa. We want to be able to go back and forth. I'm using this. This is used a lot in the internet now. You know, when you have two things and you want to exchange them, they use that. It's kind of handy. So let's do a whole bunch of examples. So far we got 8, so we can do 9. Let's say you have a to an exponent b equals c, and we want to rephrase that equation in logarithmical form. We notice that there is a base with an exponent, and that's given as an output. So the way we rephrase this is by stating that the logarithm in base a of c is equal to b. And you may be thinking, wait a minute, I thought the base was always b. Well, that's the way, yes, we started writing it out. But the important thing is to get to know the location of the things that are being involved in the equation, not just the letters. I oftentimes tell students in geometry, you know, they have the Pythagorean theorems. You know the Pythagorean theorem. You know, you got a squared plus b squared equals c squared. And I oftentimes, not to trick students, but to make sure they understand the idea, I ask students to write the Pythagorean theorem or to use the Pythagorean theorem, but I change the letters. You know, I put C here and maybe B here and maybe A there. And it's not a malicious thing. It is not that I want students to fail. No, 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 no. I just want to make sure students understand the relationship between the legs and the hypotenuse of the triangle. So when we rewrite the Pythagorean theorem using this triangle, not this one, then we have B squared equals A squared plus C squared. And some students, rightfully so, think, wait a minute, I thought the C is the one that is equal to the A plus B each one squared. And the answer to that is yes. If we're using this triangle, by all means, that is true. But if we move the pieces around, then that's not true anymore. Then we have to act accordingly. And that is part of learning concepts well versus learning them superficially. When we learn things at a deeper level, then we can move things around, and that is not going to affect our thinking. And that's kind of what's going on here. Okay. So many times we have this kind of example: b to the a equals c. There we go. Well, how do we rewrite this? Well, this is logarithm base b of c equals a. Well, what is important is not the letters that we're using, is the position of those letters, and being able to write this equation correctly using the position of the letters. It's just like the triangle. If I switch the letters around, can you come up with the correct formula? And most likely than not, you probably can. So that's kind of what we're doing here. So, and there are 6 permutations. You know, you can put A and B and C. You can exchange. Yeah, there's, so we can come up with 6 examples total just using A, B, or C. So for instance, we can put A to the C equals B. How do we rewrite this using logarithmical equations? So that would be the logarithm in base A of B equals C. So what is important is where they are, not what letters we're using actually. You can change the letters all day long, you know, and you will be able to go back and forth. Now, what if we have the logarithm in base W of y equals x? We gotta be able to go the other way from logarithms to exponential forms. Well, the base is W, the exponent is x, and then the output is y. But then if we change the letters around, we gotta be able to adjust that accordingly. This is what I sometimes call pulling the rug under you or under ourselves. W. Yep. So changing the letters around is kind of changing the problem a little bit. Can we react accordingly? Think about it. An employer would want an employee who can figure things out when things are not exactly the same way. So yeah, so if I had an employee and I gave the employee some training, and then the employee is faced with a situation that was not in the training, can that employee try to figure out things reasonably well? That's a skill that is, in my opinion, very valuable. Yeah, but also it depends. You know, there are times when that's not necessarily the case. Sometimes we want the employee to ask us what to do too. So I cannot generalize completely about that. Having said that, I think in general we do want people to think for themselves more so than just freeze and do nothing. At least if they ask, that will be, in my opinion, better. Anyway, so here we have y to the w equals x. All of this is making us more comfortable with logarithms. You know, all of this kind of exchanges between logarithms and exponential functions, because exponential functions are easier, in my personal opinion, to understand than logarithms. And so going back and forth makes things much, much more comfortable. Oh, some important properties about logarithmical functions should be addressed. So properties of logarithmic functions. So let me draw a generic function y equals logarithm base b of x. Okay. So we have a vertical asymptote. The vertical asymptote will be x equals 0. So that is a vertical asymptote. And then we have this kind of graph, which initially increases fairly quickly, but then it starts decreasing. I didn't mean decreasing. It continues to increase, but a much lower and lower rate. It takes way longer to get one increment in the output. You know, if you have logarithm base 10, you know, you go from 1 to 10, so you travel 9 units just to increase 1. But then the next time you have to travel 90 units to get to the next level, which is 2. And then you gotta go 900, well, I have to do the math, but over 900 units to get to 3. And then you gotta travel 9,000 units, more than 9,000 units to get to the next level. So it doesn't ever get completely flat, but it looks more and more flat as you go on. we always go through the point 1, 0. A point after is 2, no. B, comma, 1. And then we have b squared, comma, 1. Oh, this is interesting. Is b squared always bigger than b? And a lot of us jump to the conclusion, yes. Is b squared always bigger than b? Question mark. Many of us think, of course, how can that be? 3 squared, which is 9, is certainly bigger than just the 3 without squaring it. It is true. However, if you have 0.3 and you square that, you don't get 0.9. You get 0.09. Try any calculator. If you got 0.3 times 0.3, just do 0.3 times 0.3, multiply it out. You're always going to get 0.9. Let's do it to make sure. 0.3 times 0.3. There you go. 0.09. 0.09 is smaller than 0.3. So is b squared always bigger than b? The answer is no, it's not always. The key here is always. No, it's not always. If b is bigger than 1, yes. So the answer is yes, if, there's a big if, b is greater than 1. No, if b is less than 1, between 1 and 0. Okay, so that brings us to another kind of graph. This is the graph if b, this graph is the graph, the correct graph for logarithms if b is bigger than 1. If b is greater than 1. Very, very important requirement for this graph to happen. We're going to address the graph when b is smaller than 1 in a moment in the next page. But let's finish this up. The domain is going to go from 0 to infinity, excluding 0. So the domain is from 0, not including 0, to infinity. All of the numbers beyond 0, not 0. The range, well, this keeps going down forever, and this keeps going up ever so slowly, but still, nonetheless, always up. So the range is from negative infinity to infinity, from negative infinity to infinity as we keep going up. We go through those points. Another point here would be the reciprocal of b, negative 1. I don't want to, well, let's squeeze it in here. Reciprocal of b, comma, negative 1. Okay, make sure you get to know your graphs. Now, if b is between 0 and 1, if 0 is less than b, less than 1, then the logarithmical function does not look that way. We still have an asymptote at x equals 0, but the graph, instead of going up this way, is going to go down this way. So we're still going to go through 1, 0. We still have the same asymptote. We still have the same domain. We still have the same range. The difference is that here, we're going to have b, negative 1. b, wait a minute. No. b is between 0 and 1. So this cannot be b, because b is between 0 and 1. This is 1. So here's where we're going to have b, comma, 1. b squared is going to be smaller than b, so it's going to be on the left of it. That point is going to be b squared, comma, 2. And then we'll have b cubed, comma, 3, and so forth. So what is this number then? Let me erase it. There we go. So it is 1 over b comma negative 1. Because if b is small, remember, uh, I label a number to be small if it is between 0 and 1. If a number is small, its reciprocal is big. And what do we mean by big? Anything that is bigger than 1 is considered big. So this is bigger than 1. And then 1 over b squared is going to be even bigger. 1 over b squared. And the output is going to be negative 2, and so forth. So be aware, if the base is between 0 and 1, the graph goes down. If the base is greater than 1, then the graph goes up. Yep. Just like with exponential functions. Remember the video of the exponential function. If the base is bigger than 1, the graph goes up. If the base is smaller than 1, between 0 and 1, then the graph goes down. Yeah. And the asymptote is this. Make sure you know the asymptotes. Yep. The last thing we want to review in this video is the transformations of functions. Those transformations of functions are going to be with us for a while. So I might just as well get to remember them. Example 14, for instance. I just want to make sure the numbers are correct. Yep. Let's say you have y equals logarithm in base 2 of x. Let's see, I want to shift it to the right, so minus 1. Let's say we have this function and we want to sketch it. Okay, we know logarithm base 2 reasonably well. There it is. That was the very, very first example of this video. Okay, and then we went even farther here. No, that's a different one. So we did this. When we subtract 1 from the input, what we are doing is shifting the graph to the right by 1 unit. So the asymptote, instead of being at 0, now the vertical asymptote will be at 1. So we will have the vertical asymptote at 1, and the graph will go this way. Okay, instead of going through 1, 0 as a normal logarithm does, because of this shift, now we're going to be crossing the x-axis at 2, 0. Now, it may not hurt to compare this with the logarithm in base 2 of just plain x. So the logarithm base 2 of plain x has an output of 1 when the input is 2. But now we are already at 2, and we're shifting everything 1 unit. So now if we are at 3, we have an output of 1. For this function, if the input is 4, the output is 2. But we're shifting things to the right, so now we are at 5. For this function, an input of 8 gives us 3, but we're shifting to the right, so now we need 9. And that continues. That can be a little misleading, because if we are not paying close attention to what's going on, somebody could say, hey, wait a minute, so we're doing the square root, because the square root of 9 is 3. That's just a coincidence, because the square root of 5 is not 4. Square root of 3 is certainly not 1, and so forth. And a point here that goes with negative 1, let's think. So 1/2, logarithm of 1/2 is negative 1. But we're shifting this to the right. So now we got 1/2 or 3/2, comma, negative 1. So we're just moving things to the right. I'm assuming, and this may be a little fast for many of us, but that's okay. That's the way it goes. We're assuming that we are reasonably familiar with this function. So you know how to plot points using that function. We can stretch, we can shrink, we can shift to the left, we can flip. There's many things we can do with logarithmic functions. Practice them, review your transformations of functions, and as usual, uh, do loads and loads and loads of homework. Uh, Understanding this without doing homework is equivalent to just watching a basketball game and thinking that we know how to play basketball just by watching the game. Um, no, no, no. We need to practice. And those who know, who are pretty good basketball players, or any kind of player for that matter, baseball, whatever, they know they have to spend hours and hours and hours and hours and hours practicing. It, Even if people are talented, they still have to practice a lot. Um, so so that happens with math. We really want to practice. We want to get to know uh, logarithms very well. We want to know the differences between the equations, the transformations of logarithms, and so forth. Oh, one more thing before we finish this up. I want to graph logarithm, the natural logarithm. Um, yeah, example 15, y equals the natural logarithm of x. So the base is e, um, which is bigger than 1. So the graph looks like that. The asymptote is x equal to 0. We always have the point, unless there's a transformation, we always have the point 1, 0. And then the next point would be e. We typically actually write down e, comma, 1. And then e squared, comma, 2. And then e cubed, comma, 3. And 1 over e comma negative 1. Some people would say, well, why don't you just put e to the negative 1? Yeah, I want to emphasize that we have a reciprocal. I guess e to the negative 1 will do, but again, we want to emphasize the reciprocal aspect. If e is big, then 1 over e is a fraction, a smaller fraction. All right, so become familiar with all of these functions, and then and we'll stop the video here.